All right. So, if Mr. Hawkins, hi, that's me, starts from rest and then accelerates at 0.2 meters per second for 4 seconds, how fast will he end up going? At this point in the semester, I guess, I would recommend going through the full process, even if it feels like you don't necessarily need to all the time. That process being step 1, list your givens. And then I would start reading through the question. Starts from rest. That's a common phrase you're going to see a lot. What's that mean? What, initial what? What starts at 0? Velocity. My philosophy. My initial velocity would be 0. Like I said, you'll see starts from rest, or if initially at rest, something like that a lot. They're telling us our initial velocity is 0. We've got the acceleration given to us. And I did type it weird because I didn't want to fiddle with trying to get a fraction. So it's meters per second per second. That is true, but most of the time we'll see that written as meters per second squared. And we've got a time, delta t, 4 seconds. And we're asked to figure out how fast I'm going at the end. So there's our 4 things. Luckily, we got an equation yesterday that has all 4 of those things. We had final velocity is how fast we start, plus acceleration times time. So then I can just plug into that. 0 plus 0.2 times 4, giving us 0.8. And the biggest little mistake I saw on the not perfect pile was the units. It's just velocity, so we're still just putting meters per second. You're only going to put meters per second squared if you're talking about an acceleration. Otherwise, just meters per second. Questions there? Okay, moving on. So this, I'm pretty sure we already got yesterday, but double check, get your notes out, make sure that's in there. We are going to add a tiny bit to it today, and then have probably about half the class to chill out, and for me to pass out papers and whatnot, which for my other classes, it's about half the class for them to start doing their corrections and whatnot, but I don't suspect many of you will be doing corrections. So good job on that. We'll get to those statistics here in a minute. But a quick spot check of your notes. Everyone got this already? Oh, good. Then I'll carry right along. We mentioned the units yesterday, but I wanted to clarify how those units end up from a mathematical perspective. So if we take the units for velocity, we get meters per second. We're dividing that by the units of time, which would be seconds. So we could write that as meters per second over second. But as I've mentioned before, I really hate fractions. And here we have a fraction within a fraction, so that's hideous. I don't like it. I can't get rid of the fractions entirely, but I can condense these two. Seconds over seconds, that just combines to be seconds squared. So there we go. There's our units. Usually written as meters per second squared. Sometimes we'll see meters per second. But this is something that I would put in my notes, specifically this part. If you need the words, or if you want the words, go for it. But the main bit is the unit analysis, because we'll be doing stuff like that quite a bit in the future to help us figure out other equations once our units start getting crazier. And as people write, maybe someone here remembers, where have you first learned about acceleration in meters per second squared? Like what grade would that have been? 8th grade? 7th grade? Somewhere in middle school. Maybe 8th, maybe 7th. You didn't touch acceleration at all? Oh, all right. Interesting. Not familiar with that one. Moving on soon. think I've got one more thing to mention about acceleration. Then we're just going to quickly run through a couple problems and throw out some points. And I suspect it'll be a game of who can raise their hand the fastest to get those points, because the problems are fairly straightforward. We all good here? Okay. Then, this I also mentioned yesterday, but just to cover the basis, and it never hurts to say it twice. This is a shorthand version of the equation. You kind of think of it like a contraction. Delta V is really just a shortened version of final velocity minus initial. Delta T is a shortened version of final time minus initial. So really, this is the true equation, the truest version of it. So in that little thing, we've got 5 different variables that we can then use to solve for whatever it is we need. I don't think we ever actually have to find initial time, because usually your initial time is just 0. But we could if we wanted to, I suppose. So I would certainly have that expanded version written down if you don't already. I think we did that yesterday, but I'm not sure. We did? Okay. I see a couple people writing, so I'll give them a second. Now we'll jump into a few questions. Starting with the car initially at rest, 10 seconds later, it is moving at 30 meters per second. What's that acceleration going to be? Let's go with Jeremiah. Jeremiah says 3 meters per second. Thumbs up if you agree. Thumbs down if you disagree. All right, everyone that gave a vote agrees, so that's good. So let's check with the board. We've got initially at rest, so our initial velocity will be 0. We eventually get up to 30, so that'll go here. Again, we can say our initial time starts at 0, and then 10 seconds will just be our final. Plug all that in, and then simplify that down. 30 divided by 10 certainly gives us 3 meters per second, or 3 meters per second squared. Although, to be fair, the 3 meters per second is a little bit more intuitive, because that more clearly states that that car is getting 3 meters per second faster every single second. All good there. All right. Next up, I'm just going to let you read it, because you guys can read. Raise your hand if you think you have an answer. Going with CJ.
1.5 meters per second squared.
1.5 meters per second squared. Thumbs up if you agree with that. Thumbs down if you disagree. All right. Mostly all agreeing. We'll see what the board says. So we're starting at 0. We went up to 1.5. 1 second later, we're up to 3. 1 second later, we're up to 4.5. Remember, when we see dot diagrams like this, it's kind of like someone's taking a snapshot every single second, which is why we see these dots getting further and further apart, because they're covering a little bit of distance, then getting faster, and as they get faster, they can get further and further apart. And that will be, indeed, 1.5 meters per second squared. What about object 2? Oh, that was quick. I'm going to give everyone a second to see what they think. Then Kerrigan. 4 meters per second squared. We started at 2 this time, then went up to 6, then went up to 10. So that'll be 4 meters per second squared. And with that, assuming that continues to be true, Giovanni, what's our final velocity going to be? 14 meters per second. So far, so good? You could do this in your sleep? Okay. Maybe. Got another one. The car starts at rest and accelerates to a velocity of 10 meters per second in 5 seconds. What is its acceleration? Let's go with Isaiah. He says 2 meters per second squared. There's quite a bit of confidence in that answer. Thumbs up if you agree. Thumbs down if you disagree. All right, survey says the board agrees, so that's always good. We just take 10, technically 10 minus 0, divided by our change of time, which is 5. So that all checks out. One more, I think. As a suggestion or hint, we are in relax mode, so if you need to do a quick math check on your phone, feel free, because that's a division that I can't do in my head. I've got my pick already, just giving people time to see what they think. All right, Tristan, what do you think? Meters per second squared. All right, let's see. So if I was going to go through the process, list my givens, race car accelerates from 0, so my initial is 0, to 27, final is 27. One bit of possible confusion is they then told us that 27 meters per second is the same thing as 60 miles per hour. This book and these questions were written for us Americans, so occasionally they like to let us know a reference point, but we're not actually going to use this number because all of our equations assume we're sticking with the scientific units. So good to know, I guess, for a reference, but we don't actually need that. Our change in time, 4 seconds, and we're looking for acceleration. So like before, we'll do 27 minus 0 divided by 4, which I do believe gives us, was it 675? 6.75 meters per second squared. Do we think the board's going to agree? Hope so. Oh, good. It agrees. Seems like we're good. We will be adding some confusion to this whole acceleration business once we start talking about positives and negatives, but we're going to hold off until Monday for that because that can sometimes be a lengthy conversation. So for now, I just want to say one more thing about the notation this book uses, and then I'll pass out those tests. If I wanted to get that equation that we already have for final velocity, and multiply t up, and then from here, I would need to expand this out into what it actually means, that being final velocity minus initial, and then add my initial velocity over. But the weird thing that I wanted to mention and point out is that you will not find this equation in your textbook, at least not written like this. The textbook has it, but it writes it like that down there. It uses what I'm going to call conservative notation, meaning they go with the notation that conserves the most ink. So for one, instead of having initial, they've got a little weird 0 looking thing. It's not technically a 0, it's a naught, which is another one of those Greek letters. And it means your velocity at time 0, which is a fancy way to say initial velocity. So those are the same thing. They also left off the delta on their t, but that should really be there. And then when they go with naught, they just leave velocity as velocity. They don't put a subscript at all, but that means the same thing as final velocity. So just in case you're flipping through your book or you see this on a potential question somewhere, just know that those mean the same things. It's just different ways to write it. Their way does conserve ink, which conserves a whole bunch of money when you have to print these textbooks a bunch, I guess. But we can go with the full subscripts. All good there. Notation can be kind of annoying sometimes, but not too bad yet. Now, we have the rest of the Chapter 3 exam statistics, including our class. Also updated for first and second period because there were some people that took it yesterday and they brought the averages up, so that's good. So first period, highest was a 100. They did bring their average up to a 61, which is better, but still not great. Median 63, which is certainly better. I think it was like a 50 something before. May have been a 60, but still better, but not great. Second period, their new highest is 94, which is way better than a 75. Average 60, median 61. all in all, that puts first and second period in my concerned column in my brain. So I need to make some changes. Going to be tweaking their seating charts and whatnot a little bit to hopefully get them to be more focused. Then we get to us. Our highest was 103%, which means you answered everything right and you put something for the bonus question. There were 3 individuals that got 103, so good job to them. Our average was a 95%, which is a fantastic average to see. Makes me feel a little bit better about the other 2. And then our median, just as good, 94. So half the class got a 94 or above, and half the class got slightly below. I think our lowest grade was a B, so well done on chapter 3. Then on to 5th period. Highest 97, average 67. Still better than 1st and 2nd. Not quite as good as 3rd period. Median 75, that's puts them in my okay range. I'm okay with a 75. That average is a little concerning, so there's some individuals in there that I need to bring up. 7th period, highest 89, 62, 71. They're also teetering into the concerned column. It's always that end of the day classes, always has some troubles. But all in all, pretty good. A reminder though about corrections, which is why I said we'll mostly just be hanging out in this class period. If you're doing corrections, you work out a problem that you missed on a separate sheet of paper, you got to show your work to get the credit back for it and staple that to the original, turn that back in. The reminder though is that corrections can bring you up to the next letter grade. So if you already have an A, the corrections won't actually bring you up at all. I still encourage you to look at see what you missed, but if you did miss points and still got an A, it's probably just because you missed a decimal somewhere or forgot to put a unit somewhere. So there's not really any written corrections that you really need to bother yourself with. Just do something to remind yourself to put units and keep an eye out for those pesky negatives. But if you do corrections, we do have a couple people that got B's, I think, that could get up to an A. Those are going to be due next Wednesday. But for now, I'm going to put on the playlist because it's been a minute since we've heard it, and we're up to 105 songs. And then I'll pass out some papers. Let's go with Cameron. Pick a number between 1 and 105. 67. Classic. It's just the title of the song. You'll probably be fine.